Welcome. Today, I know this is a testing and QA conference, and I normally talk about architecture, and I'm going to talk about architecture today, but I'm going to talk about a new, unique perspective on how do you test architectural characteristics. This is something that has puzzled us for a long time in software, is how do you build architectures that you can change easily? And it turns out the mechanisms by which you use to do that heavily overlap this subject of architectural governance, which is really the way architects think about testing and quality control in architecture. And I'm going to show you some new tools and some new ways to think about that this morning. So let's say that you have some problem and you've decided you want to write software to solve this problem. So you have requirements of some kind. We don't really care how you got these requirements. Most of the things that we talk about are independent of whatever software development process you're using. But this is not the only thing you have to think about as an architect. You also have to think about all these other things. Things like performance and scalability, maybe legality if you're dealing with medical records or some sensitive information. And in fact, this is really the skill of architecture, is given some requirements and given all these other things that we have to support, we have to come up with a design that does as good a job as possible of balancing these things. You can almost never maximize all of these characteristics because they often interact with each other. I've never actually flown a helicopter, but I've talked to people who have flown a helicopter. And apparently the really difficult thing of flying a helicopter is that there's one thing for each hand and one thing for each foot, and every one of those you move affects the other, so it's a balancing act. These things are like helicopter controls in that they always interact with each other. For example, if I want to make security better, I'm almost certainly going to make performance worse because now I need to do more on-the-fly encryption, I need to do more indirection for secrets hiding, and so very often in architecture, you can't get to the best design. Your best hope is the least worst design, the least worst combination of all these things, because you can almost never maximize all of them. The other problem we have as architects is that there are a lot of these things that we could support. Here's a partial list from Wikipedia of all the system quality attributes you can support in architecture, and people always invent new ones. And one of the problems we have is that none of these are physics terms, so every company defines their own definition of what they mean by each of these characteristics. And companies invent their own all the time. One of my co-authors, Rebecca, worked on a project for a while, and the direction was to create a centralized architecture. But every design they produced, the first question was, but what happens if we lose Scotland? Because a few years earlier, a free communication outage had meant they'd lost communication with their Scottish stores for a few days, and it was very bad for them as a business, and so that became their first question anytime anyone asked them about architecture was what happens if we lose Scotland? And so the architects on that project created an architectural characteristic called Scotlandility, which is a combination of resiliency and availability and all those things that would allow them to create a design that didn't accidentally lose Scotland. What we're trying to do is add another item to this list, this idea of evolvability. But what does that really mean, to have an evolvable architecture? Well, let's say that we've chosen something like performance as a really important architectural characteristic. Having an evolvable architecture means that as your system changes over time, performance doesn't change, particularly in a negative way. And so what I'm going to describe today are mechanisms that allow you to define and protect these architectural characteristics as your system changes over time. And of course, part of that protection implies the ability to test and do quality analysis on things like architectural characteristics. But let's talk about change for a moment, because we normally think of change as just one big thing. But for us, in particular in architecture, change is two closely related things. There's technology-driven change, and there's business-driven change. Business-driven change is the kind we're most accustomed to dealing with. These are changing requirements where you start with one set of requirements and then because the market changes or you're evolving as a business, you change to another set of requirements. Or perhaps you merge with another company and have to take on all their IT and workflows. In fact, this kind of business-driven change is the subject of most books on agility and agile software development focused on this type of business-driven change. And we've gradually gotten better and better over the years at managing this kind of change. But the kind of change we've been less good at managing is this technology-driven change, the kind of change that happens to us whether we want it to happen to us or not. And part of that has to do with the world that we live in. So if you think about the combination of all the tools and frameworks and best practices and approaches and all the things that we know about building software up until about half an hour ago, that is the software development ecosystem. And this is where we all live and work on a regular basis. And it makes sense because all the pieces fit together. But we characterize this in our book as what we call a dynamic equilibrium. An equilibrium meaning that the pieces fit and it's balanced, but it's also extremely dynamic and can change suddenly without letting you know. And a great example of this dynamic nature is a few years ago when Docker hit our ecosystem. As soon as Docker hit our ecosystem and became popular, it changed our ecosystem forever. Even if you're not using Docker yet, this now creates a new set of possible decisions you can make. It changes the kind of choices that you have within this ecosystem, and it changes our whole world forever. And this is an interesting problem in software because it doesn't take a very good observer to realize that everything changes all the time in our world. All you have to do is look at the JavaScript world to see how fast the rate of change is. And it's not slowing down, it's speeding up. But this is a real problem for some roles like architects, because some architects are expected to do long-term strategic planning. But how is long-term planning possible when everything changes constantly in unexpected ways? I've literally been traveling all over the world over the last year and a half or so, and I've been meeting with many of our clients. I work for ThoughtWorks, we're a global consultancy, and I've met with many of the architects at our clients. And I keep asking them all the same question, and none of them have had a good answer for me. So maybe finally somebody today in this room has a good answer for my question, which is, can you tell me with great certainty exactly what JavaScript frameworks you'll be using 2 years from now? And of course you can't, because they probably haven't been written yet. How is long-term planning possible in a world like that? And of course the answer is it's not. But why were we trying to do that long-term planning? Well, change is really expensive and difficult, and if we can plan our way around it, then we won't have to incur that expense. But what if you built your architecture with the assumption that change is going to happen at least the rate it's happening now, which seems like a pretty safe assumption? What if you built the notion of change into your system? Now you don't have to have a better and better crystal ball because you've built adaptability into your architecture. But one of the things that we want to be able to do as we talk about these architectural characteristics is build protections for them. And a lot of that comes in the form of tests and other kinds of verification mechanisms. And that's what we're going to do today. I'm going to show you some mechanisms for building protection so that these things don't degrade over time. We, all three of us, when we wrote this book, worked as consultants, and some of us still do. And so all of our examples from the book come from real-world projects that we worked on. But we made them all generic for the purposes of the book and invented a fake company that we put all the examples against. And our fake company was called Penultimate Widgets. The chance of anyone here getting the little subtle joke here is probably pretty small. This is a sort of an English language inside joke. Many people think the word penultimate in English means really awesome because it has the word ultimate in it, but it actually means next to last. I've actually met someone in the U.S. who worked for Penultimate Consulting Company, and I think they thought it meant Ultimate Consulting Company, but it really meant next to last consulting company. And so that's the fake company name that we created for our book so that we could have something to cast all of our examples against. And this is one of the examples that happened to me. I met with one of our clients who were in the process of re-platforming their system, and they had already built up a bunch of goals for the next version of their platform. And there were 66 goals, like 4 nines of resiliency and reliability. And I remember that number so well because it was in a spreadsheet that had 66 rows on it. And I said, hey, it's really great that you've identified these things that you want to protect and support in your next architecture. But if I come back in 6 months, how many of these things will still be true? And more importantly, how easily can you tell me how many of those 66 things are still true? So it turns out that many of the things that we talk about here heavily overlap this idea of architectural governance. And this is really what QA is to architecture, is this idea of governance and not letting bad things get into your code base. So let's talk about the mechanics of that. So when you write a book like this, you have to define terms, and we thought carefully about both the name of the technique and the definition. We thought about continuous architecture, and there is some aspect of continuous improvement in the idea of an evolutionary architecture, and I'll show you some tools that support that at the end of my talk this morning. But you don't have to be doing agile software development, which this is what this implies, and so this is too restrictive. Same for incremental architecture. We thought about that, and in fact, this made it into our definition, but again, this is too narrow. Agile architecture is too broad, and in fact, like I said, you don't have to be doing agile techniques. It helps a few things, but you don't have to be doing that to do an evolutionary architecture. The closest one that we considered and then rejected was adaptable architecture. And let's talk about the difference between an adaptable architecture and an evolutionary architecture. When I say adaptable to an architect, what they think of is the configuration dialog in Eclipse or Visual Studio, or something that has a million little configuration settings, and you can adapt it for one situation versus the other. And that's not what we're talking about at all. That kind of architecture, you try to support all existing behavior and then add a bunch more onto it as time goes by. That's not what we're talking about at all. We're talking about fundamental change. So we're not talking about using one web framework and then adding another one and still supporting the old one. We're talking about fundamentally changing those things over time, and evolutionary is a much better description for that. And so here's our definition. An evolutionary architecture supports guided incremental change across multiple dimensions. And I'll talk primarily this morning about the guided part of this, although I'll describe the entire definition. So let's talk about the guided part of evolutionary architecture. Rebecca, in addition to being a consultant, she's also the CTO of ThoughtWorks, also spent some time in the evolutionary computing space. When you're designing a genetic algorithm, you're trying to design an algorithm that will produce a result and then mutate itself in a well-known way and then produce another result and then mutate itself and produce another result. If you're trying to design a genetic algorithm to produce some sort of outcome that you want, then every time it produces a result, you should give it feedback and say, are you getting closer to a good solution for me or further away? And that mechanism in the evolutionary computing world is called a fitness function. This is an objective function used to summarize how close a given design solution is to whatever your target is. So for example, a well-known problem in the machine learning space is the traveling salesman problem. Given a salesman, given a bunch of cities, I need to find the shortest route between those cities. If I were designing a genetic algorithm to try to solve the traveling salesman problem, my fitness function would be the length of route, because that's the thing I'm trying to optimize for. And so any solution that produces a shorter route is going to be better for me. And so that's what my fitness function tries to drive, is this idea of a beneficial outcome for me. What we've done in the evolutionary architecture book is taken this definition from evolutionary computing and applied it to software architecture and created this concept that we call an architectural fitness function. This is any mechanism that provides an objective integrity assessment of some architectural characteristic or combination of architectural characteristics. And I'll show you lots of examples of these things in just a bit. One of the main things here, and one of the main takeaways for you this morning, is this objective definition for things. This is one of the places we've been lacking in software architecture too long, is not being specific enough about objective measures for these architectural characteristics. And the side effect of this is once you get to objective measures, you have something you can test and see, is it true or not anymore, which allows you to make changes with confidence if you can test the integrity of those characteristics. This is the answer to the question I posed my client. If instead of defining their architecture in a spreadsheet, if they'd instead defined it as fitness functions, then they'd have not only the definition of their architecture, but also how to verify those characteristics within the same mechanism. Like I say, I'll show you a bunch of examples of those in just a second, but I want to finish my definition first. The second part of which talks about incremental change. And there are two interesting aspects for us about incremental change. One of them is how you put new things live architecturally without breaking the things around it. I'll show you how this works in the abstract, and then some specific tools for this at the end with a case study. And the second part of this is using tools like continuous integration and deployment pipelines as a way of applying these fitness functions on a regular basis to make sure that every time you make change to your software, you're verifying all these important architectural characteristics are still intact. The last part of our definition talks about multiple dimensions. And this is really just the pragmatic awareness that if you're talking about evolving software systems, you can't just talk about the structure and architecture of those systems. And so you'll see in our definition here things like performance and auditability and scalability and legality, which are very common things that you think about in architecture. But we also include things like security, because sometimes that has an impact on the way you think about designing or changing your architecture. And one thing we definitely include is relational database design. In fact, we have a chapter in our book on evolutionary database design, because you cannot evolve your architectural structure if you cannot evolve your database at the same time. And I'll show you how this definition of multiple dimensions gives us a brand new perspective about architecture and really the scope of where these architectural characteristics live. I'll talk about that in just a bit. So there's our definition, and evolutionary architecture supports guided incremental change across multiple dimensions. Let's dig into this idea of guided change a little bit more deeply. One mistake that some people make is thinking that this is some brand new framework that you could download and start using. And I'm going to show you a lot of new tools this morning, but this is not some single framework. In fact, many of the tools that you use to implement fitness functions have been around for a very long time. It overlaps many existing things that we already have in our world. Things like metrics. I'll show you unit testing libraries that let you implement fitness functions. Brand new things like chaos engineering, monitors in the DevOps and operational world. All these things can be used to implement fitness functions. And I'll talk as well about how do you differentiate between fitness functions and things like unit or functional tests. So one of the things we did in the book is categorize all these fitness functions. And some of these have to do with mechanisms like scope. Atomic fitness functions look at a single characteristic in architecture, whereas holistic ones look at a combination of architectural characteristics. This is about how you invoke them. Triggered fitness functions are run like unit tests, whereas continuous ones run as monitors and just run all the time within your ecosystem. We would prefer as many of these as possible to be automated, because that, of course, is the secret to having a lot of automated governance running in the background, so you don't have to think much about it. But we also realize that some of these will necessarily need to be manual as well. Some of them have a static outcome, like a true-false or a single number value, but some of these fitness functions are dynamic as well. For example, when you look at something like a scalability is usually a combination of number of concurrent users and performance. And it's generally okay that as the number of concurrent users go up, performance goes down some, but I don't want it to fall off of a cliff. And so I can set a range of acceptable values for performance under heavy load. That's dynamic and based on the load, but it's still objective. And that's one of the key parts of my definition, is objective measure. There are also time-based fitness functions. And I'll actually show you an example of one of these in just a second, of looking at some characteristic over time to look for interesting trends. One of the questions we get, and I think is going to be very interesting for this crowd, is do we have any such thing as a domain-specific fitness function? And this is the good place to talk about the distinction between fitness functions and more traditional kinds of testing and verification mechanisms for projects. Because I'll show you in just a moment a unit testing library designed to test fitness functions. And so now the question is, well, what's the difference between one of these and a regular unit test? The difference is, and this is the good way to separate these two concepts, is that fitness functions only look at architectural characteristics, nothing about the problem domain. So for example, when I talk about elasticity or elastic as an architecture characteristic, that means that I can handle a burst of users coming in all at one time. I can talk about elasticity purely in the abstract. It could be a gaming site or catalog site or streaming video site. And so that's something that you would write a fitness function for. Anything that requires knowledge of the problem domain should be written as a unit, functional, or user acceptance test. And so there are architectural characteristics that are purely in the abstract, and then there are the solution to the problem you're trying to solve, which require domain knowledge. And this is a really good way to separate these two concepts. If you require any domain knowledge, then it's a unit, functional, and or user acceptance test. If you can talk about it purely as an architectural characteristic, then you would consider that purely as a fitness function. So let's look at some examples of these. This is still pretty abstract, I realize. Let's look at some actual tests and code and how you would implement some of these things. And I'll talk about a few of the categories that I've just established. So let's look at an example of an atomic triggered fitness functions. These are, look at a single aspect of architecture, and they're triggered like unit tests. So here's a great example of this idea of a fitness function. So let's say you're an architect and you're building a component-based system of some kind. One of the things you want to try to avoid are cyclic dependencies between your components. This is where one component talks to another component, which talks to a third component, which talks back to the original component. This is an anti-pattern in architecture because it makes it difficult for me to reuse one of these components because they're coupled to other components. But it's also extremely common, particularly in in languages that have powerful IDEs like Java or .NET. Because you're coding along in your favorite Java IDE and you reference some class that you've never referenced before in this file. What does your IDE do for you? Pops up a dialog and says, do you want to auto import that for you? And you swat that away so fast now you don't even see it anymore. It's like a sneeze reflex now. If I came over 5 minutes later and say, did you just auto-import something? You'd say, no, I haven't auto-imported anything all day, I swear, because you don't even realize you're doing it anymore. But what you're doing is accidentally tangling up all of your components like this. But this is a real headache for architects, because how are you supposed to prevent developers from getting into this bad habit of swatting away that auto-import dialog? Are you supposed to stand and look over their shoulder as they're coding, and as soon as they do that, go, hey, you just auto-imported something and you're messing up my architecture? This is one of those examples of something that's important, but it's not urgent, and so it very often falls through the cracks. So as an architect, the way you prevent this is you write a fitness function that prevents this. This is using a very old metrics tool in the Java world called JDepend, and it understands the structure of Java packages, and you can write a test that says, tell me if there are any cycles in my code base or not. So as an architect, you can put this into your build, and now when a trigger-happy developer accidentally creates a cyclic dependency, they're not allowed to check that code in because this fitness function has prevented that from happening. Another example, also at the very low-level code level, directionality of imports. Let's say that as an architect you want to establish some rules that say things like, well, it's okay for persistence and web to import util, but I never want a developer to accidentally import all of web into util, because I have a direction of how information should flow in my architecture. Here's how you prevent that. This is also using JDepend. There's a similar tool in the .NET world called Independ. And what this allows you to do is define rules in your architecture about how things should be wired together, and then this verifies that that wiring is correct. And so again, if a developer accidentally does something backwards, this will catch it before they can check that into your code base. So these are two examples at the very, very low code metric level. Let's look at another example, also of an atomic triggered fitness function, but this time at the integration architecture level. This is a common problem when you have extremely dynamic architectures like microservices. So let's say that we have 4 independent project teams here, and the team in red is providing some overlapping bits of information to all 3 teams on the right. The architectural concern I have here is if all 3 or all 4 of these teams are evolving aggressively, how can I make sure they're not going to start breaking the integration points? And so that's the architectural concern I have, is preserving those integration points between those teams. So how can you do that in a way that doesn't have them constantly checking with each other? The common engineering practice in this world is called consumer-driven contracts. The idea is that each of the 3 teams on the right will put together a set of tests, and there are a bunch of testing frameworks for this. One is called PACT, P-A-C-T. Another is called PACTO, P-A-C-T-O, because it was written in Brazil, and that's the Portuguese version of the word PACT. The 3 teams on the right put together a set of tests, hand it to the red team on the left, and the red team promises, I will keep those tests green all the time. And those tests are the things that establish the contract between these teams. So that if the red team changes and doesn't break any of the tests, then that's cool. They changed in a way that nobody cared about. If it does break one of those tests, this becomes a placeholder for conversation. Hey, let's get these 2 teams back together and reestablish this contract, so that we can safely move ahead and be as aggressive as we want with changes without constantly worrying that all that aggressive change is going to break something that's going on. And so I'm preserving that architectural characteristic of integration points. Triggered holistic fitness functions are ones that are triggered like unit tests, but look at a combination of architectural characteristics. So let's say, for example, I have a medical system. In the US, we have a law called HIPAA, H-I-P-P-A, which is the Health Insurance Patient Privacy Act. It has all these rules about how long medical information can stay on screens and how you have to encrypt it, et cetera. So let's say I was building a medical application and I was trying to achieve high scalability. And one of the ways I did that was to use caching. And by using caching, I can get my level of scalability. I have another fitness function in the same project that's looking for staleness of data, which is one of the things that HIPAA prevents you from doing, is keeping data around too long. And when caching is turned off, that works perfectly well. But when I turn on caching and then look at staleness of data, it starts failing. And this is the classic example of architectural characteristics interacting with each other. So sometimes you want to execute them in combinations. And that's this idea of a holistic fitness function, are combinations of these things that can be run together to make sure that things work correctly. Atomic continuous fitness functions look at a single characteristic in architecture but run all the time. And a great example of these are monitoring tools in the DevOps space. Tools like Nagios, for example, is a great tool that lets you not only monitor performance, but also establish thresholds and raise alarms if you fall outside those thresholds. That's exactly a fitness function in our terminology, is you've defined a performance metric and you set up a trigger or an alert as to what happens if you don't actually meet that performance metric. This is a common practice in the microservices world when you want to test something like performance in a production system and you have a large complex combination of things like microservices using synthetic transactions. This is where you insert an artificial transaction into your ecosystem and then trace it and monitor it to see how long each interaction takes and how long the total transaction takes, and then throw it away at the end. But it's a good way to test production systems. In fact, this is the common advice in the microservices world, is use synthetic transactions to test things like performance in production systems. Very common. The last and most complicated of these, of course, are continuous holistic fitness functions. These are things that run all the time and look at combinations of architectural characteristics. And the best example we have of one of these that already exists out in the world is Netflix's Chaos Monkey. And what they eventually open sourced is the entire Simian army. So I'm sure you're familiar with the Chaos Monkey because it started an entire new branch of architectural consideration and QA, this idea of chaos engineering. They worried as they moved all their infrastructure to AWS, what happens if, because they don't own their infrastructure, what happens if it starts misbehaving? And so the original Chaos Monkey just calls general chaos. And then they got much more specialized. The Chaos Gorilla simulates an entire AWS data center going down. That actually happened about a year and a half ago where Amazon East went down because of a misconfiguration. And while Amazon East was down, Netflix stayed up because of the Chaos Gorilla had already simulated the entire data center going down. This guy, latency is one of the biggest headaches on AWS instances, so that's the latency monkey. He goes and squats on an instance and drives latency really high. The janitor monkey cleans up instances that we don't need anymore, that we've evolved past. He'll actually make an appearance a little bit later today. The doctor monkey checks the health of services, looking at CPU utilization, et cetera. But the two that are most interesting to us, for my purposes, are this guy, the conformity monkey, and his close cousin over here, the security monkey. The conformity monkey is how Netflix engineers enforce governance rules in their architecture. For example, if the Netflix architects decided that every service should respond usefully to every RESTful verb, then you could build that into the conformity monkey. And every time it would check a service, it would ask it all 4 verbs. If it didn't respond correctly to one of them, it would kick it back out of production. The security monkey is an even better example of this because it scans each of the services for well-known security vulnerabilities. And this starts really highlighting the real purpose of this idea of a fitness function. It's not to have a group of architects and other engineers go in a room and come up with new ways to torture developers. It's a checklist. So a few years ago, a very influential book came out called The Checklist Manifesto. And it was about professions like airline pilots and surgeons who use checklists heavily. And it's not because they don't know their job or because they're forgetful. It's because at really, really detailed jobs, it's easy to forget important steps. Now, every developer knows that you're not supposed to release your container with the debugging port still turned on. But where is that on their priorities list? Is that in the top 20 or the top 30? Because you're thinking about a lot of things when you're trying to get code running. I got to get this feature working. I got to get environment debugged, and I got to figure out what's going on with that logging thing and all this other stuff. So this is really just a checklist that architects and QA can put together in collaboration to say these are the important things in architecture that we don't want to accidentally skip because we're in a hurry doing something else. And this is a great example of being able to implement those really important things, and they just run in their ecosystem all the time, checking that these important things are being done. So let's look at more examples of this idea of fitness functions as a governance mechanism, because that's really what architects call QA, is governance, governing all those things in architecture. One of the things we're trying to encourage architects to do is to get rid of vague, meaningless terms like this. We've gone too long in the architecture space with too much vagueness like this. And what I'm asking architects to do is drill one level deeper into this. What do you mean architecturally when you say maintainable? Because there's nothing objectively measurable there. Remember, we're trying to get to objectively measurable things. So here are objectively measurable things that relate to maintainability, complexity. Having a less complex code makes it more maintainable. Consistent naming conventions throughout all of your code makes it more maintainable. Controlling things like coupling, which is something you can measure, makes it maintainable. Things like Postel's law, which talks about how you extend things intelligently, makes for a more maintainable code base. So let me talk about how you'd wire up something like one of these metrics as a fitness function. And this also supports my contention earlier that many of these techniques are not new at all. Some of them have been around for decades. We just recently started calling them fitness functions and realizing they're all very closely related to one another. So several years ago, I was working with an insurance company in the U.S., and the architects there were very concerned about the code quality because they had a lot of very junior developers, and they were concerned about the quality of code these junior developers were creating. And this one junior developer had been given a task that had a server-side piece written in Java and a client-side piece written in JavaScript. And being a sort of a bad developer, it was something to do with all 50 states, and being a kind of a bad developer, ended up writing a method that was basically if state is Alabama, then do something for Alabama, else if state is Georgia, do something for Georgia, for all 50 states, in one big giant method. But the architects on that project had wired into continuous integration this metric called cyclomatic complexity, which measures how complex a function or method is, and then set a threshold for all of their projects at 50. And I'll tell you exactly where they got that number, because that's a monstrously high number. There used to be a metrics tool in the Java world called crap4j that looked at a combination of code coverage and cyclomatic complexity to try to determine how crappy your code was. And if your cyclomatic complexity ever got to 50 or above, no amount of code coverage would make your code not crappy, in the opinion of that tool. And so that's where they set that magic threshold, and this developer accidentally hit that by writing this overly complex method. Now, my friend Glenn Vanderberg has a great quote that bad developers will move heaven and earth to do the wrong thing, that the amount of ingenuity that really bad developers will put into creating train wrecks is amazing. And if you take half that ingenuity into solving real problems, the world will be a better place, but that doesn't happen for whatever reason. And so this being kind of a bad developer thought, how can I solve this problem? Oh, I know how to solve this problem. I'll just write that code in JavaScript instead. And so that's what they did. Just wrote it in JavaScript, basically the same method, but the architects outsmarted them because they had a cyclomatic complexity check on the JavaScript code too. When they tried to check that in, it failed, and they went to the architect in great frustration and said, look, this stupid code base won't let me check anything in, and that's the day they learned about the strategy design pattern. Now, I'm not suggesting this is the best way to teach people fundamental software architecture patterns, but it is a good way for architects to be able to establish boundaries and thresholds around important architectural characteristics so that they don't just run wild on your project. Here's an example, a few examples of some really nice tools that exist in this space. This is a tool called ArcUnit. It was specifically designed to be to work hand in hand with JUnit. In fact, if you've used JUnit, you can already use this, and it uses some of the helpers from the JUnit world. Here's a great example. It comes pre-configured with a bunch of governance rules already. One common annoyance by architects are lazy developers who throw generic exceptions because whoever catches that exception doesn't know where it came from because there's no context, because it's generic. So how can you as an architect prevent lazy developers from throwing generic exceptions? Here's how you do that. No classes should throw generic exceptions. That's a pre-built governance rule already in ArcUnit. Another example of something you might want to govern is, let's say that we as an organization have chosen a third-party logging package. How can we make sure that people don't use the one that's already built into Java? Here's how you prevent that. No classes should use Java util logging. I mentioned naming conventions earlier. Here are tests around naming conventions to make sure that we have consistent naming conventions and we don't do things like put interfaces in the same package as the implementation if we want to separate that. But here's an even deeper example. Let's say there's an architect. I want to design a layered architecture with a distinct presentation layer, business layer, and data access layer. When I design that, and then hand this over to developers to implement, how can I make sure that they don't cheat on my layers? The common thing that happens here is that some developer says, well, requests are taking too long going all through all those layers, and so I'll just cheat and go directly from the presentation layer directly to the database. But as an architect, that ruins this design and in fact chips away at the reason you created that design, but it's really hard to police this unless you build a fitness function for it. This is using the Hamcrest matchers from the JUnit world. So you can write these really fluent assertions like this. No classes that reside in a package service should access classes that reside in a package controller. Many architects have written almost that exact same English sentence in a wiki somewhere or SharePoint portal, and it was right once, read never by another human being. You wrote it down because it was an important principle that you wanted to establish in your architecture, but where is this on the developer priority list as they're trying to get things working and environments debugged and things shipped and schedule pressure? I mean, it's there somewhere, but top 30, top 40, by implementing as a fitness function, you give this principle teeth. And people cannot ignore it anymore. On software projects, we have things that are both urgent and important. But we also have things that are important but not urgent. And not messing up the structure of my architecture is important but not urgent. And this allows you to address those important things that get away from things that are overly urgent. Now, ArcUnit is written specifically in the Java world. In December of this last year, inspired by ArcUnit, Ben Morris released NetArcTest, which lets you write the same kind of tests in the .NET ecosystem using the same style of fluent matchers. So controllers should not directly reference repositories. Only classes in the data namespace should have a dependency on system.data. Naming conventions and all those other sorts of things. So here's another set of tools that are well suited for writing these kind of architectural quality assurance around architectural characteristics. These are all very low-level structural kind of things. We also interested in things like performance, for example, in architecture. This is an architectural characteristic. And performance is interesting because you as an organization have to decide exactly how you want to implement this. For example, you might look at the average response time as your important performance metric. This is if you care about the average experience for your users. And notice that when we define this, we want to have a concrete objective number in this definition. Because once we do that, we can test it using monitoring tools and a bunch of other facilities out in the world. So rather than just saying, well, we want to perform an architecture, specify how you want that performance to be. And so here's an example of using cumulative response times just as a point in time. But maybe you also want to look at a trend line. Trigger an alert when the average response time continues to increase over a 2-month period of time. This is an example of that category I talked about earlier of temporal fitness functions that have a time component. And so here what you're going to do is wire up an environment so that every time you make a change to the code, it's going to put it into a staging environment and do a performance check on it using something like Lighthouse or something like that, and then write that value into a database. And then what this fitness function looks for is the trend line in that database over a period of time to see if it's continuing to constantly rise. A lot of teams are starting to look at specific performance budgets around numbers like page render time. If you can't render your page usefully in 3 seconds or less, there's an unacceptable number of users will get bored with your site and wander away, particularly on mobile devices. There's a complete page draw time, and all these can be automated and measured with tools like Lighthouse to check things like performance. You may also look at things like maximums and look at outliers. Maybe that's the thing you care about in terms of performance. You also can look at things like scalability, and again, every organization has to come up with what their definition is. But we're encouraging you here to come up with concrete numbers for all of these metrics, because once you have concrete numbers, then you have a way to automate these tests and verify them on an ongoing basis. Sometimes you can find really nice tools to do this kind of stuff. Sometimes, though, you just have to wire up your own workflow. So here's an example. I worked for a company a financial services company that used a handful of open source libraries and frameworks. And one of the lawyers got worried about viral licenses in these tools and frameworks. And so we went and found all the license files for all these open source tools and let the lawyers look at them. And then one of the lawyers asked an awkward question: what happens if one of these libraries updates the terms of their license during a software update? And this has happened in the past. The Qt user interface library did this, and so now this is something we have to check for. And so what we ended up doing was building a mechanism that we took the license file out of every one of those open source libraries or frameworks, took the entire file and hashed it and put that value into a database. Then anytime one of these libraries updated itself, we went and grabbed its license, hashed it, compared it against the value in the database, and if it changed, we called the lawyer. Let the lawyer look at the new thing, make sure it's okay, and vet it, and then put that value in the database and move forward. So we basically built a mechanism that triggers and lets us know anytime something that important has changed in our ecosystem. Now, since we've done this, a bunch of other tools have come out to allow you to do the same thing, like Black Duck software and some others, but that's a good example of wiring together your own mechanism for handling something like a fitness function. So I'll wrap up by talking about how you put this stuff into practice. The first thing you do is identify dimensions that are interesting to you from an architectural standpoint. And this is really a prioritization exercise. What things do we need to preserve over time? What are the most important aspects of my architecture? Once I've identified those things, then you define fitness functions for each dimension. This is your protection, the mechanics of protection for each of these architectural characteristics over time, creating objective definitions for them, let you test them continually. And then finally, using deployment pipelines or continuous fitness functions to automate the application of these things. Deployment pipelines and continuous integration make a great place to apply these fitness functions. And while a lot of this happens at the beginning of a project, this is meant to be an ongoing living part of your project. Just like unit and functional tests are a living part of your project, you keep this updated because this is really the living definition of your architecture. The last thing I want to talk about is this incremental change business, which I haven't talked much about. And there are two aspects, as I mentioned before. One, I just touched on this idea of using continuous integration and deployment pipelines as a way to apply these fitness functions on a regular basis, including some that you can apply globally in your organization around things like security and other global concerns like that. But the other example of incremental change has to do with how you put things live in operation. So let's talk about that in the abstract, and then I'll talk about some specifics. So let's say that you have a website. In the book, Penultimate Widgets had a website, and it sells widgets, and there's a star rating service running that allows you to put star ratings on things. And one day, they released a better version of star ratings, which allows half-star ratings. And they put it live. They didn't force anyone to start using it. This is just now a new capability in their architecture. And over time, the services that need star ratings are going to migrate over to the better star rating service. One of the magic tricks Netflix taught us about architectures like this is you monitor not only the services, but also the routes between services. And any time you find a service that no one is routing to anymore, you can disintegrate that out of your ecosystem. It turns out that's the job of one of the monkeys. That's the janitor monkey in the simian army is responsible for doing that, finding services that no one's routing to anymore because they've evolved past them, and then kicking it out of production so it no longer takes up those resources. So my last example, I noticed there's a talk coming out from Uber about moving fast as well. This is a great example of this idea of incremental change at the architectural level. This is from the GitHub engineering blog in an entry called Move Fast and Fix Things. GitHub is a very aggressive, agile engineering organization. They average 60 deploys a day. They do continuous deployment. And this describes a particular problem they ran into around merge. So it turns out since day one at GitHub, the way they've merged two files together is to shell out to a shell script, tell command line Git to merge them, and then suck that back into GitHub. And that works great, it just doesn't scale particularly well, and these guys operate at really extreme scale. And so this is about their effort to replace merge with their own in-memory version. So they wrote their own in-memory, more efficient version of merge, and they did their testing on it. But now here comes the scariest part of my talk. Now they have to put it live. But here's the problem. You can't break merge on GitHub. It's literally never had a single bug logged against it ever. And the last thing you want is some Tuesday afternoon for bugs to start showing up in something like merge. But this is a really serious, common architectural problem. How do you make surgical replacements in architecture without causing rippling side effect breakages other places? The way they did it and open sourced it so you can take advantage of it is to create scientists. And they've open sourced this to about a dozen other languages now. And what scientist allows you to do is conduct experiments. So it has two blocks, a use block and a try block. The use block is the old stuff that we're currently replacing, and the try block is the brand new stuff we're trying out. And so when scientist hits one of these experiment blocks, it always runs use, and that's what the user always gets returned to them. So the worst case scenario, if you fall into one of these experiments, is you get exactly the answer you would have gotten back before. But then you can configure it as to how often it also runs try. And so in 1% of the cases, they also let it run try. When it runs try, it randomizes the order in which try and run are executed, so you don't get timing issues, measures the durations of everything, compares the result of try to result of use, swallows and records any exceptions, and then publishes all this stuff to a dashboard. So here's when they first went live with this experiment. You can see at 2:20 a.m., they're doing a little over 2,000 merges. If you looked very carefully at the bottom, you can see some tiny little red tick marks. So let me zoom in on the bottom. Here are places where try and use disagreed. And so here are places that they have bugs in their code that this hasn't impacted their users at all yet because they've still been getting the old code returned back. But now they can go in and fix those bugs at their leisure. One of the other things they were checking is it better performing? And it turns out it is. The green line is the new code, and the blue is the old code. They ran this experiment for 4 days until they had 24 hours with no slow cases or mismatches. Over the course of that 4 days, they did more than 10 million comparisons between the old code and the new code. So when they left that new code in place, they had really high confidence it was doing exactly what they wanted to do. So a few final observations here. Most fitness functions are local to projects, and they're global when you can apply them to every single project. So we're trying to avoid creating architect police states here. We also want teams to collaborate on this as well. For architects, developers, testers, QA, business analysts, all should collaborate on this. Again, we're trying to avoid this kind of architecture police state. We're giving architects a sharp tool here, but it's a tool to protect architecture, not build a very locked down world. We obviously prefer automation here, but can rely on manual when needed. In many ways, this is a new way of thinking about defining things like architecture and QA around architecture, because the fitness functions really define what your architecture looks like in a very objective, concrete way. And it gives you a new way of thinking about prioritizing things, and also a new way of thinking about the cost of things, because now I can tell you how much performance costs in my architecture. It costs how much it takes to implement and maintain my performance fitness functions. So I'll point you to one last resource. We have a website called evolutionaryarchitectures.com. It has a bunch of resources on it in addition to the book, including a resources page, which has a link to every one of the tools that I talked about here today is on that resources page. We also have a bunch of more examples of our fitness functions under a link called Fitness Function Katas. So you can look at that and get a good example of the scope of what we're talking about from a fitness function standpoint. I'm out of time, so I'll just say thank you very much for having me. I hope you enjoyed it, and I hope you have a great conference. Thank you.